All right. Hi, everyone. Hello. So the midterm is gonna be after reading week, as you probably have seen. So the way, unfortunately, because of, or fortunately, depending on how you look at it, because of how the deadlines were structured, I was kind of forced to schedule the project one to be due after reading week. I understand that you're busy anyway right now, so I guess we'll have kind of office hours in the second half of reading week and stuff. So the midterm is gonna build on project one. So you should do project one. And like I said in 180, like obviously you can get solutions, in a way that's not exactly the same as what you would get on the midterm. That's probably not in your interest because on the midterm, there's no ChatGPT or anything. So also just submitting ChatGPT output is an academic offense. Probably won't catch you, but we do. Yeah, so don't do that. Try to do it from scratch. So similarly, try to make sure that you've done all the labs up until that point from scratch. I don't think there's going to be a new lab assignment the week after reading week, because that's the week that project one is due and the week that we have project one. So basically, in terms of kind of the core practice, this would be the labs up to now, the online exercises, and of course, project one. So you can look at the midterm here. So I think, but I'm not 100% sure that we'll be able to cover everything from last year's midterm up until the date of this year's midterm. So in particular, if you look at it, so linked list, I hope to do tomorrow, but we'll see how things go. So question one, you still cannot do. Question two is straight from the lab. So that is totally something that you can do. Question three, well, if you're done project one, essentially, if you look at question three and project one, question three is kind of like a very kind of, well, not very, but like a simplified version of one aspect of project one. So that's like that. That's just still question three. So question four was not a popular question, but essentially it's kind of from the pointer exercises, right? So if you look, I don't remember the exact number, but basically you have a pointer exercise where what you want to do is you want to have a block of pointers to structs. So that's basically this exercise. And then question five, we've been doing on Monday and we'll continue doing today. I think that's the last one. Gotta be. So one thing that we haven't done up to now is the terminology abstract data structure. I will do it formally, I think probably after reading week, because there are things that are more urgent right now. You can just ignore it for now. It's just kind of a piece of verbiage. It's not really core to the midterm. So basically, except for question one, and depending on whether you are already done project one or not, you can look at the midterm right now. Again, like with 180, I think what you saw is that if you can do the labs from scratch and if you can do the extra exercises and you know what happened in lectures, you're basically good. So it is important to, make sure that you can actually do things from scratch, because a lot of the time in the lab, like it's completely legitimate to work with partners and stuff, and completely legitimate. That's why they're there, to get help from the TAs. But if that's how you got the answers, you might be kind of misled into thinking that you're ready when you're really not. So that's about it. So I think kind of one piece of feedback that I got last year is that People wanted kind of more short questions and fewer long questions. So I will take this feedback somewhat. It's important to realize that there is always a trade-off when you're designing a test between putting in, well, three things. So you can put in short questions that don't necessarily reflect the kind of thing that you actually want people to have learned, right? So it's not actually a useful real-world skill to be able to answer like short format midterm questions. So kind of that pulls me towards kind of putting something more substantial that's kind of more like what you do in the labs, more like what you do in the project. So on the other hand, there is the time constraint. And then also there is the thing where, why don't you just put like 2 long questions and be done with that? Well, it's because if a student misses one of the questions for one reason or another, like they misunderstood the writing or the question relied critically on like some piece of information that the student doesn't have, if it's one of 2 questions, the student is going to do really badly on the exam. So that pulls me towards making the midterm longer. But if I overdo it and put a lot of long questions on the midterm, people are not happy either. For one reason or another, they shouldn't actually be. So at least kind of my approach, and I think explicitly or implicitly, it's everyone's approach, is a midterm is a way to measure people's progress, right? So any measurement initially, it's not going to be calibrated, right? So there is no way to write the midterm and say, oh, like that's going to be like a 75% average midterm. There's just no way. So for that reason, what people do is they, try their best, but, I don't know, like maybe it's gonna, so kind of usually I'm pretty accurate about guessing kind of what the performance would be, but I could be like easily off by like plus or minus 5. So, then, after the fact, you look and say, okay, like this question turned out to be really challenging. This question turned out to be really easy. So on balance, how should the thing be adjusted? And sometimes you adjust, sometimes not. Okay. Questions about the midterm? Anything? All right. So I want to go back to what is basically Q5 from the midterm, right? So we are defining this pi_int structure. The way we defined it is we have a buffer of digits. The digits are stored in reverse order. So 190 is stored as 091. And what we want to do now is the thing that we promised to do last time, which is implement the plus plus function. Right? So plus plus, what it wants to do is it takes a pointer to this pi_int, and it changes the length and the buffer in such a way that the number that's contained is larger by 1. Okay. So we are over here. So we'll call it plus plus. So when you're writing something that's a little bit complicated like that, what you want to do probably is draw a picture and say, this is what I want to happen, right? So I want to say, if I start with 190, meaning I start with 091, I want to say, when I add 1, what do I want? Well, I want 191 over here, right? So you just do long addition, right? So except it's reversed. And you'll see why it makes sense that it should be reversed. But for now, like +1 is really easy, right? You just say 0 plus 1 is 1, and then 9 is still 9, and then 1 is still 1. So what about if there is a carry? So let's say that it was 199. So that should become 200, right? Okay, so 199 plus 1 is 200. So we wanted to result in this. So how would it work? So we're adding 1, and we're saying 9 plus 1 is 0. And if you remember from school, you carry the 1, right? So then 1 plus 9 is 0 again, because you again carry the 1, and then 1 plus 1 is 2. Right? So that's the algorithm. We're just adding 1, so it can't get too complicated. So one complication that we haven't accounted for yet is, what if it's like 999 plus 1? Then you need to add an extra digit, right? So let's do that. So we want 1000 now. So what happens is, well, 0 carry the 1, 0 carry the 1, 0 carry the 1, and here is your 1. Oh no. Oh, that's unfortunate. Okay, so is that recording? Yeah, it is recording. So what we briefly did in the board here is just said we'll keep track of the carry, and initially it's going to be 0. And then we'll modify the digits in the buffer. So if the buffer is initially, I'll do a different example, something like 991. Then what we'll say is carry carry one trick is to just set it to 1 initially, because we're adding carry plus the current digit plus whatever we're adding. But in this case, we're always adding 1. So I'll just set carry to 1 initially, and then I'll keep going while carry is not 0, right? So like 1 plus 9, so that's 0, and carry is still 1, and then 1 plus 9, and that's 0, and carry is still 1, and then 1 plus 1, and that's 2, and 199 plus 2 is 200, plus 1 is 200. So we're done. All right, so let's implement that. So we'll start with carry being equal to 1. And that would be the location in the buffer. And we'll keep going while So we'll keep going while the carry is not 0. Right? So if carry has become 0, then that means that we are done. So it also might be that I has become p length, in which case we're done because we need to put the carry at the end. All right, so the sum is the current digits plus carry. So initially we set carry to 1 to just simulate that we're adding 1, because initially actually carry is 0, but we're adding 1 at the bottom. So then we'll say, okay, so what's p buffer? So p buffer is the last digit of the sum, right? So you're adding 1 digit, buffer I, and the carry. So that's going to be a number between 0 and 18. Right. Because carry can be 9 at most, and the digit can be 9 at most. So it's between 0 and 18. So we just need the last digit of sum. If sum is between 0 and 18, then we can just do sum mod 10. In fact, for anything, we can do sum mod 10. And then carry is going to be 0 if the sum is between 0 and 9, and it's going to be 1 if the sum is between 10 and 18. So sum divided by 10 is going to do the trick, right? So it's integer division. So if sum is smaller than 10, then it's just going to be 0. It's larger than 10, or equal, then it's going to be 1. All right. So at this point, what we've done is, if we started with something like 991, then we got to the sum. If we started with something like 999, then we changed the 9s to a 0, and the carry is still 1. So we can say, okay, if we're done, but the carry is still 1, well, that's defeatist. We're not going to say overflow. We're going to add another digit, right? So I'm going to say, okay, so p buffer realloc and make the length be 1 larger. Right. So going back, why is it like this? Well, the type of p buffer is int star, right? So buffer is a block of integers. So and it's a block of integers with this length. So what we're saying is we want for the length to become larger. So that means that the length of this block should be length plus 1 times size of it, because each integer that we use to store a digit uses up that. And then we're saying, okay, now it should be length plus 1 times that. So, okay, so we reallocate that. So now we are allowed to say p buffer at p length so that's got to be 1, right? Because the only way that you're extending a number by adding 1 more digit is if you started with like 99 or 999 or 4 nines or something. So the rightmost digit is going to be 1. Don't need to check. And then we'll increase the length by 1 as well. All right. So that's the plus plus. So let's write something in order to be able to test it. I actually already declared a function that's for that's print pi_int. So this is just kind of to print the number that we're storing here, and it can be kind of arbitrary length, right? So print pi_int. It's going to take a p. And what we're going to do is we're just going to print the digits in turn in reverse. So I'm printing a decimal, and that is the ith digit from the end. So I'm starting from the last one. After that, I'll print a new line so that like print pi_int works like kind of the default Python print where it prints it on one line. All right. Questions about any of this? All right. So let's try using it. So we set pi_int to 190. So we'll say print pi_int, and we'll print p. So this code actually is worth pausing on because there's different. So there is the star, there is the ampersand, there is just the plain p, and it so happens that it's all correct. It's amazing. So how did it happen? So just a quick review. So we're saying initially p is just a random chunk address, right? So p is of type pi and star. So that means that p stores an address of a pi_int. That's what it means that p is of type pi and star. And initially p is, yeah, so it's sometimes called the dangling pointer, is like nothing in particular because we didn't say, we said it's an address, but we didn't initialize it. Some people prefer to say something like p equals 0, and that's just to make sure that they know that p is like an address, but you put a 0 in it. It's not actually an address of anything right now. So then we said to create pi_int, change the value of p such that it contains an actual thing, right? So in order to do that, we had to have sent the address of p because otherwise create pi_int would not be able to modify the value of p from 0 to something new. So that's one way of saying, well, like if create pi_int is supposed to modify p, it's got to be that it gets the address of p. There's no other way. another way of thinking about it is if you're saying create pi int over here, well, this guy knows what's up, right? So it expects an address of an address. Why does it expect an address of an address? Because it wants to set the address of the, so it wants to set the address that you declared in main to be an address of an actual pi int. In order to do that, it needs a pointer to that variable. That variable happens to itself be an address. So that's why it's a pointer to a pointer. Again, it's kind of a lost cause, but I'll repeat that the words double pointer are just banned in this class. And the reason I do it is because I don't think saying, oh, it's a double pointer is illuminating, right? I think the way to make sense of this is to say, well, we have a value that is a pi int star, and we're wanting to send a pointer to that to the function. So then inside the function, we say, okay, well, like star p will make it be this. Okay. So going back here, so address of p is of type pi int star star. So that's a mnemonic I can get behind. Address of adds a star. The dereference operator removes a star. So address of p here makes it so that this is pi int star star. Does that make sense? And then inside here, when I'm saying star p, well, p here is of type pi int star star. So star p is of type pi int star. Again, important. So I think most people are clear on this at this point, but important to realize. So two different things that the star is used for. So here, the stars are part of the type, right? So P is of type pi int star star. Sorry, not part. P is of type pi int star star. So here, what I'm saying is go to address P and get the value there. So they both have to do with addresses, but that's the end of the similarity, right? So this star here and those stars here, different jobs. The jobs of, so those are parts of the type. And this is an instruction, go to that address and get the value. So again, you can, so this is kind of like not thinking things through the time doors. So like int star, so like if you do like int a and then you do int star pa equals address of a, and then you do int star star ppa is address of pa. So you can do like star pa is of type int. And that's because, well, one way to think about it is this star cancels out this star. And so that's because that star is on the left-hand side. Or the more correct thing to say is, well, it's address of A and star address of A is just back to A again. Right? So the same as star address of A, just because address of just gets literally canceled by the star. So you're saying, get me the address of A, and the star is saying, go to that address and get the value. So that's the same as saying A. So both of those are the same as A. So if you say something like star star PPA, also of type int, and also the same as A. Interesting suggestion by Copilot. So if you do not actually true. So oh, it is. Yeah. So it is true. So if you do this, so address of PA and then star, so that's the same as PA, and then star PA is the same as A. So same as star PA and also same as A. can do star PPA, and that's type in star, and that's same as PA, and same as address of A. So of course, because of what PA is equal to. And you can do address of PPA. What's the type of that? Okay. Yes. Oh, we did manage to confuse Copilot. It's actually in star star star. Okay. But that's just the address of PPA. So kind of go further because we haven't defined anything further. We could, in principle, also define like in star 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 PPPA, whatever. All right. So all right. So that was that. So now we're back to that is what we want because set PyInt takes a pointer to PyInt. Print PyInt also takes a pointer to PyInt. So just verify. So print PyInt is like this. So we just send a P there. Plus also does this. Print also does this. So let's run this and hopefully it works. Cool. So it printed 190 and also printed high, which I did not want. So now we can do a plus plus thing. Add PyInt is not implemented yet, but plus plus is. So I'll say plus plus P. And what I hope is that it would print 191. No. Cool. All right. So we did a plus plus. What it had done is it went into P buffer and changed the P buffer to be 191. So why are we bothering? Well, the idea was that we want to be able to store integers of arbitrary length, right? So let's try setting it to like 999 and see that it doesn't crash. It very well might. Well, it didn't crash. However, it overrode this 9 with a 1. So, and it did not rewrite any of the zeros. So that's a little bit weird. So let's see what's happened. So here we were like, if carry, while carry, well, yeah. And here we said P buffer sum. So sum was supposed to be, yeah, that was supposed to work. So let's just put a breakpoint here. And let's run this.
You're not declaring I as 0 to start. And
oh,
you're also not plus.
Yeah, those would be problems. Okay, so I initially was, well, it happened to be 0, but that was not guaranteed. And we did not increase height by 1, so we weren't advancing. Thank you. So let's run it again, and maybe we don't need to debug. All right, thank you. So that worked, and it extended the thing by 1. So I did not forget to increase the length. I did not forget to increase the length. So that should be fine. So that you could do without anything. The point is now I can add like as many times as I want, and it's still going to be good. So how should I do it? Let's just do addition. So now that we have plus plus, we can kind of one way to do it, one way to do addition, and that's what was required in the midterm. Actually, like it wasn't an addition of two actual integers. It was like the pi integer plus a c integer, and then yeah, exactly. You could do just plus in a loop. That was the idea that people would do that in the midterm, right? So you don't actually need to write anything extra. But here let's do actual addition. So it's not that hard now that we have plus plus. So what was it called? So okay, so at pi end. Okay, fine. So I already promised to do that. So okay, we'll do the silly thing and do add. So add pi end value. So that's like not the most efficient thing, but that's fine. You can do the efficient thing on your own. So we'll just say for int I equals 0, I smaller than value, plus p. We're done. So again, worth kind of noticing that here it's pi and star p, here it's just p. Why is that? Well, it's because this is again the type, right? So you're sending a pointer to a pi int to add pi int. So here it sends on the pointer. So p here is of type pi and star. It gets sent on to plus plus. Right? So the star has not gone away anywhere. It's just that it's part of the type. Does that make sense? So when I say plus plus and I send the p, it's going to be again of type pi and star. So okay. So that compiles. So now we can do whatever. So I'll just add like 1,000,000 times 1,000,000 and see what happens. So it take a while. So that's going to be like this. And I need to declare int the first time that I'm running it. So it's thinking, and that's because like this is like a slightly slow algorithm, not the most efficient thing. So let me just do it 1,000 times for a start, and let me just add like interesting digits here. And then I'll print pi int at the end. I think that should be, so that's like 1 billion addition, so 1 billion plus pluses. So that might also not be immediate, but eventually it's, yes. So here's my billion, right? And you know, like you can do this with an unlimited amount of digits because, you know, like once you round out the digits, it just reallocs and the buffer becomes larger. Right? Make sense? Questions? All right. So I don't really have anything complicated that they can do right now. So are there questions that people have? If not, I'll just take up a few pointer exercises, I guess. Yeah.
So I asked for some gaps about, I think that car star and the car array were the same, except for how they split the roads. Is this true for other data types?
Well, that's not even true about car stars and arrays. The commonality between car stars and arrays is that you can initialize them with string literals, but that's the one that's basically the commonality, right? So you can say car S1 is ABC, and you can say car S2 is DEF. So this is just shorthand for this, right? So it's a car array that you're initializing with this, and C just gives you this convenience of not having to write this in curly braces. So this is different. This is saying put the string ABC somewhere in memory, and then make S1 be the address of the A. I mean, that's your mistake. So pointers are not the same as arrays, right? So arrays get converted to pointers when used. So that means that when you're saying something like S2 at 2, then what happens is this is the same as S2 plus 2, and S2 gets converted to the address of the first element. Right, so in that way, because S2 gets converted to the address of the first element, they kind of behave similarly. So a difference is that if you declare an array inside a function, so if you say something like, so that does not make sense. But S2 will not be a valid address outside the function. Right, and that's because S2 is an array that's a local variable in the function. So you can remember, you can like write down what the address was of the first element of S2, but S2 is not anymore going to exist when you exit the function. On the other hand, if you do something like this, that is fine. Right, and that's because the DEF is an actual string literal. It's going to be placed somewhere in memory, and G is going to return the address of the DEF that you placed somewhere in memory. Yeah.
I mean, I was wondering, when you're initializing an array with a string, is it still a constant car star? I can't remember if you can change it.
Yeah. So the answer is like it's literally shorthand for this, right? So yeah, totally. So so like the reason is you're copying them into S2, right? So here it's just that you're saying I want those 4 cells in memory and put D in the first one, put E in the second one, and so on. Here you're saying put this thing, which as you say is a const car, and then give me the address of that. So then you're not allowed to go to that address and modify the car because it's actually a const. Right. There was something here. No. All right. I will see you tomorrow. Thank you.